All right, so this week we're going to finish up looking at logarithms. We should also be starting chapter 6 towards the end of the week, which is on trig. So that's going to be kind of like a brand new start. But in a sense, that's good because anytime we start a new chapter, it's usually very basic stuff at the beginning and then harder stuff towards the end. So end of the week will probably be easier than what we do today. All right, first problem, just to kind of warm up and remember our rules for exponents. I just want to start off with this example. I want to rewrite this so that we don't have one big exponent. We're going to break it up into individual terms. And the first thing I want to focus on is the plus and the minus. Okay, so first thing is we've added 2x and 3y. When would you take and add exponents? What's the rule for that? When do you add exponents? Yep.
When you multiply.
Yeah, multiplying things with the same base. Like 2 cubed times 2 to the 5th. That's 2 to the 8th. Okay, so you add exponents when you multiply. So what does that mean this part would have been originally if we break up back into its factors? Yeah, DJ?
That'd be a 2x
Yep.
times a to the 3. Do we just take the 3 and 3y?
3y, yeah, that whole term is what was added. So if we multiplied those together because they have the same base, we would add. And when do you subtract in an exponent? Yep.
Division.
Yeah, when you have division. So that means we would divide by a to the z. Right, so that'd be a to the 2x plus 3y minus z. Right, so we've got a to the z, but we have a to the 2x and a to the 3y. Okay, I don't want the 2 and I don't want the 3. So now, what are we doing with the 2 and the x here? What operation? Multiplying them. What's the rule for when you multiply exponents? So we have a rule for when we add, when we subtract. Does anyone remember when you multiply? Brett?
So you have to add.
No, not adding. Remember that? Yeah?
Do you move to the front, like 2a to the x? No, okay. Never mind.
No, well, I like the idea of moving things to the front. We're gonna do that in a little bit, but not this one. When would you multiply two numbers together in your exponent? Okay, what if I had something like this? How do I do that?
X squared times x squared times x squared times x squared.
Yeah, and what would it come out to?
X to 10?
And what's 5 times 2?
10.
So that's when you multiply. Anytime you raise a power to another power, you multiply those two together, and that's your exponent. All right? So how could I rewrite a to the 2x? Thinking about it, starting with this. What would you do to a to the x to make it a to the 2x?
So a to the x squared.
Yeah. Okay, so there's a to the x. Do the same thing with a to the 3y, make it a to the y cubed. Now we've got a to the y, and the bottom is a to the z. Okay, so that's purely just practicing rules of exponents and rewriting and manipulating things a little bit. Okay, questions on that? All right. Right, so we're going to look next at another example we've already done. Okay, so you have this in your notes, except when we solved it, we did it graphically. Okay, now we're going to see if we can do it algebraically. All right, so I'm just trying to do some examples to use some of the rules we learned last week, just to refresh them. Okay, so this is the example where we have a town with an initial population of 50,000. It's going up at 2.5% a year. When will the population hit 100,000? All right, well, first thing I need is my equation. I'll write my population as a function of time. Okay, does anybody remember what the equation is? And it's got that, and actually, you know what? The 100,000 we use after. That's going to go on a different side. Yep, Brad?
It'll be 50,000 times 2.
So I like that part. That's good. Initial amount times, what goes here? Give you a hint. Yeah, 0.025 is part of it. And a 1, and one more thing.
Squared. No, to the t.
To the t, yeah. Right. Now, that's just your basic equation. So now if you wanted to solve it graphically, you'd put up 50,000 times 1.025 to the t in y1, put 100,000 in y2, and then what would you do?
Intersect.
See where they intersect. Okay, that's graphically. So now we're going to do it algebraically. Okay, so first thing I'm going to do is replace p of t with 100,000. So 100,000 equals 50,000. And I'm going to add these up, 1.025 to the t. All right, our goal is to get t by itself. But does anybody see one thing we could do to at least move to the other side? Yeah.
Subtract 50,000. Or is that divide by 50?
That's divide because this is multiply.
Right, so divide by 50,000.
Yeah. So divide each side by 50,000. That's gone. And on this side, just cross out as many pairs of zeros as you can. So what am I left with on the left? 2 equals 1.025 to the t. Now, why can't you just solve this using basic algebra? Like add, subtract, multiply, and divide. What makes this equation different? It's not something you'd see in Algebra 1.
The variable is in the exponent.
Right. The variable is an exponent. If it was just this would be easy. We just divide each side by 1.025, and we'd be done. Okay, but now we have a variable and an exponent. Yeah.
Is it log it?
Yeah. Okay, what we want to do is we'd like to be able to move this exponent to the front, but we can only do that if we have what? Yeah, if you have a log equation. So what I'm going to do is take the log of both sides. Okay, so the log of 2 equals the log of 1.025 to the t. And now I can put the t in front. Okay, until I take the log, I can't do that. So we have log of 2 equals t log 1.025. And what would be my last step to get t by itself?
Divide by log 1.25.
Yeah, divide by log 1.025. And that's the answer to t. Okay, we'll just plug it in and see what we get as a decimal. So take log of 2 divided by log 1.025. So log of 2 divided by here we get about 28.07, and that was in years. Okay, so it's going to take about 28.07 years for the population to double. Okay. And if you look back in your notes in some section in chapter 5, we did that graphically, and that's what we got. Okay, so it's not that hard to do algebraically. Okay, just involves a logarithm. Questions on that? Okay. So last thing in 5.4 part 2. Okay. Does anybody remember doing that in Algebra 1? Like you got a set of data and you draw a line to it? called a line of best fit or line of fit. Well, how come a line of fit wouldn't be appropriate for this data? I mean, you could, but it's certainly not the best for some reason. Yeah.
Because it's a curve.
Yeah, I'd say the data, I don't know, I think it follows more of a path like that. Okay, it's kind of starting off slow and then it curves up. Yeah, so this is basically an exponential curve, right? And we can model that with what's called a power function. Okay? And a power function has this format. Y equals ax to the m. Now, when we do it, we're going to do a little bit by hand. We're also going to try something on the calculator. The thing on the calculator is it uses different letters. So I'm just setting it up the way the book uses it. The calculator is going to use different letters. I think it uses A and B instead of A and M. All right, so this is called a power function. All right, so really what we got to do is decide, first of all, before we start doing a problem like this, if a power function is even the right way to model the data. Okay, there's all kinds of different models. Maybe a half parabola would be a good way to do it. Maybe a cubic. We don't know. Right? So I'm going to show you how you decide if a power model is what you want to use, and then how you do it. All right. So I'm going to show you a trick. I'm going to take this equation we just had. Make sure I use the same letters. And we're going to do something we just did before. We're going to take the ln of each side. Right? Now, once I take the ln of each side, what can I do with my exponent there on the right? Yeah, I can take and just put it in front. Well, actually, no, sorry. We need to split it up first. Then we can put it in front. Let's do it that way. Okay. Since that's a product. Okay. Remember when we combine and split logs, a product splits as a sum. Okay. A fraction splits as a difference. So this is a product. Right. So what I did is I split it as ln a plus ln x to the m. Now I can put that exponent in front. Okay, the only way I could put it in front the way I was going to do it originally is if I had this. Both the a and the x were raised to the m power. Then I could put it in front. But because it's just x to the m power, I need to split it first and then move it. Okay, does that kind of look like anything we've seen before? Get back to Algebra 1. If you remember that. If not, I'll cross some stuff out, and then I think it'll look close to something, yeah? Yeah. Okay, don't cross this out on your paper. I just want you to see it. But if you cross out all the ln's, you basically get y equals mx plus a. Okay? Or b, whatever letter you want to use. All right? So what that basically means, or what we can say, is that ln of y is the linear function of ln of x. And it's like we have a slope of m and a y-intercept at ln a. Right? So this idea right here is how we decide if we should use this method to model the data, if we should be using a power function. Right? And it all has to do because of this end result. We got something that kind of looks like y equals mx plus b. Right? So when we try to decide if we should use this method, it's going to have to do with looking for a line. Okay? Or graphing something and looking for a line. Okay, does everybody have that? All right. So let me show you how we determine if a power model fits the data. Okay. What they're going to give us is a table of x's and y's. Okay. I'll scroll back up. Let me scroll down so you can see what they're going to give you. So they're going to give you a table just like this. Okay. And the first thing they ask is a power model appropriate for this data? Okay. The first thing we're going to do is take this table, and we're going to take the ln of every value in that table. Right? So we're going to set up a new table. Right? And it's going to look just like this. ln x, ln y. Okay, so we have 8 things we need to find. And in these spots, it's going to go the ln of every number. Okay, and then we're going to have this table. In that new table, we're going to graph the points. If the points look like they are a straight line, then a power model is what you should be using to model the data. If we find that new table and we graph the points and they're not in a line, then a power model is not the right thing to use. What is the right thing? Depends on the data. Okay, but the ones I give you, this is going to work. Right? We're going to do one that works in class. Okay, and once we find our power, once we decide a power model is the way to go, we'll find our Y-intercept. It's kind of like finding B. Then we'll find our slope. And then we'll write our final answer. Right, let me just double check. I think when I wrote it, I used y equals, was it ax to the m? Are those the letters I used?
Yeah.
Yeah, so it depends if we want to be consistent with what the book does or not, or with what the calculator does. The calculator is going to use, I think it uses A and B. So what might be simpler, I would say in this case, if you want to instead of call that A, okay, that's what it really is. If you want it to match up with the equation we used earlier. Okay, or take the equation we used earlier and call it y equals bx to the m. It doesn't matter. It's just our variable. Right. So once we have our y-intercept, and then once we have our slope, then we're going to simplify. Okay? And we're going to end up with an equation that looks just like that. Our final answer isn't even going to have an ln in it. Okay, so I'll show you how to do it by hand, and then we'll do one on the calculator. All right. So step 1, first determine if a power model is appropriate. So we need to create a new table taking the ln of every x and y value we have. Okay, so I'll do the top ones. If somebody has their calculator and can just type in the bottom ones, that'll help us out a little bit. All right, so we have ln of 1. Okay, that gives me 0. Okay, ln of 3. And just round these to the nearest tenth. We're going to graph them. I mean, we can only graph so precise. 1.1. Okay, ln of 5. About 1.6. And I'm also going to use ln of 5 again down here. And lastly, ln of 8. Okay, about 2.1. All right, ln of 5 I already got for the y's. How about the ln of 31.2? 3 point what? All right, we'll go with 3.4. All right, how about ln of 73.1? 4.3. And the last one, ln of 160. 5.1. Okay, let's graph these points. And if these points are in a straight line, then a power model is the way to go. Okay, after we graph them, we're done with this table. We don't need this table for anything else. We can get rid of it. Okay? This table is just to see, should we use a power model. All right, so let's make that nice and big. All right, so we got 0, 1.6. You're about right there. 1.1, 3.4. 1.1, 3.4. Okay, 1.6, 4.3. 1.6, 4, 3, maybe about right there. And 2.1, 5.1. 5.1. Okay. Overall, do those points look like they're pretty straight? You think, yeah. I mean, if we were to put a line in there, they're pretty close. I'd say if anything's not close, it's probably because of my graphing. All right, but by hand, I think it looks like they are a straight line. All right, so I think a power model is the right thing to use. Okay, so next, we're going to find our, basically, Y-intercept of this line. Okay? So we're going to find what I called A. Okay? And to do that, I would fill in this point. In our formula, fill in 1 for x, fill in 5 for y. In that formula. So 1 for x, 5 for y. What did I say for x? 1. We did this a minute ago. What's the ln of 1? 0. And 0 times anything?
0.
So what we did is, the reason I picked that is because I knew I could get rid of my m. Because I had 2 variables and I can't solve that. Right? So if you have to do one by hand, that's how I'll probably have it set up. Okay, so you could get rid of the m just like I did there. If that doesn't happen, I'm going to let you use the calculator to do this. All right, so I get ln of 5 equals a. Okay, that's like my y-intercept. Okay, and just to kind of show you where that is, that's about 1.6. And that's where my line crosses the axis. All right? So again, we don't have to think of this table anymore, but if you want a connection to it, you just found the y-intercept of this line, okay, which is part of this final answer. Okay? In fact, it has to do with that part right there. All right, next thing we need to find is m. Okay, for that, I would pick another point in the table. Just don't use the same point again. Which point do you think I should pick? Yeah, I would do that just because it looks like those are exact values. These look like they're rounded off. All right, so this is going to be x is 8, y is 160. Would I say x was 8 plus ln 5? All right, first thing I can do to get m by itself would be what? I wouldn't divide yet. Think of it if you just have this.
Minus 5.
Yeah, you'd minus the 5. So what are we going to minus here?
The ln 5.
Yeah, you're going to minus the ln 5. So that's gone. Oops. ln 5. Okay, now we have rules for combining that. We can do that. ln 160 minus ln 5. Okay, if you subtract 2 ln's, what does that mean this would be if you recombine it? how would subtraction come up here?
Division.
Yeah, we must have had division 160 divided by 5 originally. Okay, so that's ln of 32. Okay, and what would be my last step to get m by itself? Olivia?
Divide by ln.
Good. We're going to divide by ln 8 and divide by ln of 8. So we get m equals ln of 32 divided by ln of 8. Any questions on that? All right, now let's just type that in and see what we get. Ln of 32 divided by ln of 8. Right? I'd like you to write that as a fraction. So what is that as a fraction? 1 2/3, or we can just press fraction, convert it to improper. It's 5/3. Okay, so now let me show you how we plug these in and we can end up with our final answer. All right, so we had ln of y equals m ln of x plus ln of, what was our intercept? 5. All right, what's the first thing I could do here? It's kind of the opposite of something we just did with this 5/3. Let me see, Corey, you see what I can do with that 5/3? Think of our rules with logs. What is a number in front, really? It's an exponent. Okay, so put that back as an exponent. So, DJ, what would that be? Ln of
X to the 5/3.
x to the 5/3 plus ln 5. Okay. Now, Tom, what can I do on the right hand side?
You can combine them.
Yeah, whenever you have addition of two logs, you can recombine them. So addition means that these two things originally must have been what? Okay, think of our addition here. What would you have to have originally? You would have had what?
You need a 5x.
5x.
More than that.
5 times x to the 5/3.
5 times x to the 5/3. Okay, if you have multiplication, that would split as a sum. And now, if we're allowed to take the log of both sides, we're also allowed to cancel it out from both sides. Okay, so there's our equation. Y equals 5x to the 5/3. Right? That's the equation that if we were to graph this and graph the points, it would go right through them perfectly. All right, so now I'm going to show you same thing, except we'll do it on the calculator. Okay, any questions on how we did it algebraically? All right, so on the calculator, first thing we need to do is type in our table of data. Okay, we need to type this in. Does anybody remember which button you press to do that? All right, so first thing we got to do is click Stat, and we want to edit the list of points in the calculator. Okay, on mine I don't have them typed in. Some of you might from the last class. But basically what you do is put your x's in y1. Right, so we got 1, whoops, 1, 3, 5, and 8. You don't have to put the x's in y1, but this is the easiest way to do it. And then put your y values in L2. So we're using L1 and L2. 5, 31.2, 73.1, and 160. Okay, so any question on getting the table in the calculator? Okay, next step is we got to tell the calculator what kind of model we want it to find. Okay, the calculator could find a line, it could find a parabola, it could do whatever you want it to do. We want it to do a power model. So you're going to go back to Stat. This time you're going to go to Calc and scroll down until you see the one that says Power Regression. All right, so on mine it's option A. It says PWR regression. You're going to press on that. Now, as long as you typed your x's in L1 and your y's in L2, don't mess with the x and y list. Okay, I'll come back to what this is in a second. Don't worry about the equation. Just go down to calculate and hit enter. Now, notice the calculator is approximating things because these values are decimals. Okay, they're not exact. So what value do you think the calculator really should have gotten for A? Should have gotten what? 5. That should be the number in front of x. And for B, it's really 1.6 repeating. So if you do this and you see the same number repeat 4 or 5 times in a row, chances are that decimal should just keep repeating because of the accuracy of the data in the original table. Okay? So that's how you can get the exact same thing on the calculator. Yeah?
What kind of normalization R squared?
If you have an R squared, that's okay. It's telling you how good of a model the data is. It's probably says 1. Does it equal 1?
Yeah.
What, 0.999? Yeah, that value is telling you, you decided to use a power model. This is how good the model approximates your data. 0.999 is almost perfect. Yeah. Okay, I don't have that because I turned it off. Yeah.
When I do the power, whatever, it doesn't come up with that. It just has,
And did you hit enter?
yes.
You hit enter again?
It doesn't have that list on it. It's just, oh, no.
Okay. All right, so now let's just graph it and see how good of a model it is just by eye. I'm just going to type in 5x to the 5/3. Okay, if you want, the calculator can type it in for you. If you go to VARS, statistics, regression equation. That answer we just calculated. Remember it said REGEQ on the screen? That's where it stored the answer. It doesn't round them off, though. It's not going to type in 5x to the 5/3. It's going to type it in exactly the way it calculated it. Okay? If you want, just type in 5x to the 5/3. Okay? But the calculator can remember it and type it in for me. And now on y equals, I'm going to turn on my stat plot. So I hit enter, and now it's highlighted. And for a window, what was my highest x value?
80.
Okay, so maybe 0 to 10. What was my highest y value?
180.
All right, so let's go 0 to 200. All right, let's just see what I messed up.
Your minimum was 200.
Oh, thank you. So let's go 0.
You did it again.
I did it again.
No, you just
got it
got
backwards.
I'll get it. There we go. So there's my points, and there's the curve going through it. Okay, and we can speed it up a little bit. All right, so it's a pretty good model for that data. Okay, any question on how to do that? Okay, one on the test I'm going to ask you to do. You will be allowed to use your calculator, but I will not show you how to do a regression the day of the test. That's a regression, what we just did, power model. All right, so make sure you know what option to use, power regression. questions on exponential power regressions? All right, so last thing we'll do, much less involved with the calculator, doing stuff we've done before, just graphing, finding domain range asymptotes, okay, that kind of stuff. All right, up until now, we've only been able to type 2 bases into the calculator. What are the 2 bases the calculator has buttons for? Graham? 10 and E. Okay, if you want base 10, you use log. If you want base E, you use ln. Okay, you can also turn off your stat plot. It's just going to confuse us if we keep it on, so I'm going to get rid of it. Okay, well, here is how you can type in a base other than 10 or E. There's 2 ways to do it. I would just pick one of these 2 ways and remember it. Okay, I'll show you both work, but you only need one. So basically what you do is you take the log of your argument and divide by the log of your base. It doesn't matter if you use common log or natural log. It'll work either way. So let's say you wanted to do log base 2 of 7. Okay, you don't have a button for base 2 on your calculator. So the way you have to type it in, log of 7 divided by log of 2. Okay, and that's common log. Or if you type it in ln of 7 over ln of 2, you get the same thing. Right, so if I just simply asked you on the test, what's log base 2 of 7? This is how you type it in. So we've got log 7 divided by log 2. That's it. It's 2.80. Now, if you wanted to do it with ln's, okay, same thing. ln of 7 divided by ln of 2. Same answer. Okay, and this is called the change of base formula. Okay, any questions on that? Okay, change of base formula is helpful when we have to graph something that's not base 10 or base E. Okay, we have to use that formula to do it. Okay, so this one I want you to graph log base 3 of x, and then find domain and range. Okay, so how would I type that in? Log base 3 of x. Yeah, Corey? Perfect. Log of x divided by log of 3. Okay, now for our window, remember we said the argument can't be negative. So in this case, I wouldn't look past 0. Okay, x max. I mean, we could probably go up to 50 because logarithms grow so slowly. That's going to be fine. Y max, even 10 is way more room than we need. Okay, let's just hit graph. Okay, and there's our log function. Now for y min, you know what? I do want to set that a little lower. Everybody see that it does go below the axis here? If I zoom in, you can probably see it even better. Okay, and as I type in numbers closer and closer to 0, it does go lower and lower. Let's type in something extremely close. And I'm at negative 27. Why can't the calculator show it, though? It almost looks like the line just stops. Yeah?
Because it gets close to a straight line.
Yeah, anytime it gets close to vertical, the calculator has trouble graphing it. So this graph, okay, should really continue down just like that. Okay, and what do we have here? Something that it gets closer and closer to. Go ahead.
Vertical asymptote.
Yeah, there's a vertical asymptote right there. Okay, because if you try to, I typed in 0.0 and then a bunch of times and then a 1, but if I type in 0, undefined. Okay, again, an error. All right, so there's our complete graph. I would say for a window, that's fine. Okay, just use that as your window. That was 0. And what about the domain here? How far left and right does this function go? Yep.
So it would be, down to 0, or on the,
Are you talking about mean opened or closed?
yeah.
Like include or not include?
It'd be
Well,
not include, right?
yeah, not include. And how high? To infinity. So it's an unbounded interval, not including either end, 0 or infinity. How about the range? About how high and low is it going to go? Yeah, every log function is negative infinity to infinity. Okay, even if you flip it and it went the other way, it would still be negative infinity to infinity. Even if it flipped vertically, it's always negative infinity to infinity for the range. Okay. Questions on that? Right, so we found our window, that's the complete graph. Got the domain, got the range. Okay, transformations work exactly the same way they've worked in every function we've done all year. Okay, let's just make sure we remember what each one of these does. Okay, and you do them in the order that I wrote, A, B, C, then D. Anybody remember what A does? There's 4 things we can do. We got 2 shifts and 2 stretches. So if you get it wrong, there's only 3 more to pick from. Okay?
Horizontal shift.
Good. It's your horizontal shift. And remember, it's backwards. Plus is going to shift left, minus shifts right. Okay. How about B? Yep.
Horizontal shift.
Yep. All your horizontal stuff is in here, and it's all backwards. So in this case, smaller numbers like 1/2 or 1/3 actually stretch it. Bigger numbers like 5 or 6 compress it. Right? Now we're going to get outside the function, outside the argument, and look at C and D. Okay, what does C do? Yep.
Vertical stretch.
Vertical stretch. And then the last thing is our vertical shift. What else can B and C do if they're negative? Flip it. Okay. B would be a horizontal flip. So horizontal flip would look something, if you just had a picture like this, it would look like that. So that's a flip over the y-axis. And then if C was negative, that's a vertical flip. That's a reflect over the x-axis. All right, so kind of using what we just went over, I want to know basically what the negative is going to do. So just one thing. Put a negative in front of x. And then I want to find the domain range and vertical asymptotes. Right, so to graph log base 3, the base doesn't matter. As long as you're comparing base 3 to base 3, all you have to do is look at the transformations. You're going to take log base 3 of x, and what's that negative going to do? Oh, heaven? It's like putting a negative where B is. Yeah? Which way is it going to flip it? Over which axis? Yeah, it's going to flip it horizontally over the y-axis. So to graph that, you would take this one and flip over y-axis. Okay, so now let's find our domain and range. Well, my range before was negative infinity to infinity. If I flip it, what's my range now?
Negative infinity.
Okay, it's still negative infinity to infinity. How about my domain, though? It's going to be going in a different direction. So, yeah.
Negative infinity to 0.
Yeah, now my domain is negative infinity to 0. If you want to see a picture, we can just graph it. Let's do zoom 6. All right, and there's your picture. Okay, so still going to go up and down forever, but now all the x's go towards negative infinity. And where's my vertical asymptote here? Yep, x equals or y equals? X equals. Okay, so we found everything they wanted. All right, next one, another transformation question. But how might you want to think of this a little differently? It's not written in what I call this standard order here. Yeah, Corey?
Well, negative x plus 30.
Yeah, I would think of it that way, and then you can see the two transformations. One of them we just did. Now we've got an extra one. All right, so we have two transformations. How about Olivia? Can you tell me my first transformation? Well, what do you think you have to focus on first, the negative x or the plus 3? All right, so that negative is going to come second. That's b.
Okay,
So,
plus 3.
yeah, first thing you want to focus on is the plus 3. Right?
Horizontal shift.
Yeah, which way?
Up 3.
Which way is
No,
it?
that's sideways.
Yeah, horizontal. You want to think left and right. So you're.
Right 3.
Does everyone agree right 3?
No, left 3.
Yeah, left 3. Remember, horizontal does the opposite of what you think.
Okay.
So plus is going to go, now I'm confused, left 3. I forget which one you said first, but it's left 3. Is there any question on that? You might have said that at one point. All right, so that's going to shift left 3. And then the negative in front of the x. Somebody remind me we just did it?
Flip over the y-axis.
Yeah, that's a horizontal flip, which means it's over the y-axis. Question?
So you're okay with us just writing like shift left and that's right horizontal shifts?
No, as long as you give me the direction and how much. Yeah. If you wrote shift 3, I would mark that wrong.
Just like vertical shift.
Okay.
Horizontal shift.
All right, so just make sure you say the direction and how much. Okay, or the axis and what it's doing. Don't just say flip, because flip can be 2 ways. All right, so when we have to graph log functions by hand, it's helpful to find the intercepts if they exist. Okay, some of the graphs we've looked at maybe don't have a y-intercept, okay, but you're always guaranteed to have an x-intercept. Okay, it'll always cross the x-axis somewhere, but maybe not the y-axis. Okay, and our vertical asymptote can move. So it's helpful to find that as well. Because if you can get that vertical asymptote, basically your log function either looks like that or like that. I'm not going to grade you on how sharp you draw the curve or anything like that. All right, we'll just plot a few points and sketch. Okay, so all you have to do to find out where the vertical asymptote is going is look at your horizontal shifts. Okay, shifting up and down has nothing to do with a vertical asymptote. Okay, think of a vertical asymptote. It goes up and down forever. So if you shift it up, It's still going up and down forever. But if you shift it left and right, that changes where it is. Okay? Look at the argument, because that's all the horizontal stuff, and set that equal to 0. That tells you where your new asymptote is. Okay, and if we do want to find intercepts, okay, remember your x-intercept is when y is 0. Your y-intercept is when x is 0. Right? We can use the calculator to do some of this for us. Okay, and if you need more points, use your table and get more points. Just remember that the graph of a logarithm only goes in one direction. So make sure you pick points in the direction it goes. If you don't, you're going to get an error. Okay. Can't take the log of negative numbers or 0. All right, so this part, use your table and your calculator. All right, so let's see if we can sketch that. Log base 2 of 3x plus 5. First thing I would do to sketch it is just find that vertical asymptote. Figure out where that's going to be. Okay, what's my equation for the vertical asymptote? DJ?
3x plus 5 equals.
That's it. Just set the argument equal to 0 and solve. So we get x equals negative 5/3, which is about negative 1.7. Yeah. For graphing purposes, I usually round to a tenth because I can't graph any more accurate than that by hand. All right, so let's put that in. Okay, so vertical asymptote at negative 1.7. It's probably good enough. And now from here, okay, all I'm going to do is type in my function, and I'll get some additional points on my table. Okay, try to get what this curve is going to look like. Is this going to curve to the right, or is it going to curve to the left? Which way?
Right.
Yeah, the basic function always curves to the right, unless you put a negative in front. That's the only thing that could flip it. There's no negative. So it's still going to curve to the right. All right, so I already know it's going to be way down here. I just need to get an idea of how high it's going to go. All right, so let's type in our function. Okay, remember, you got to type it in using your change of base formula. Log of the top. Divided by log of the bottom. Use our table. All right, so when x is, see, 0, we're at 2.32. So, all right there. Okay, when x is, let's go out to 10. We're at 5.1. Okay, and that's probably good enough. Okay, just sketch your curve. Just try to make it somewhat smooth. Let's see how we did. Okay, any questions on why, again, we're having this issue where it's not showing the graph? Okay, so don't, if you were to sketch it like that on a test, I'd mark that wrong. That's not how it looks. Okay, it should continue down. Just like that. Right, and what else do they want? Domain, range, and asymptotes. Okay, what's my domain here? Think about what your asymptote is, and then it's everything beyond that. Yeah.
In parentheses, -5/3.
Yep. pick anything from your asymptote to the right, just don't include the asymptote. Range, we've already said it goes up and down forever. That's every log problem. Unless you do something funny like this. Okay, that might change the behavior. That would look kind of weird. But we're not doing ones like that. And our vertical asymptote, we already had x equals negative 5/3. Okay, questions on that one? All right, and let's look at our last problem. Okay, this has to do with what's called the Richter scale. Has anybody ever heard of that before? Richter scale? What are they? Generally earthquakes. I don't think they use it for anything else. Okay, but the Richter scale measures basically how strong an earthquake is. And the intensity of the earthquake depends on three things. Okay, we don't really need to know the physics behind these things, but if you just want to know what they stand for, R is the magnitude. So usually you hear a number on the news like a magnitude 3.5 or 6.2, something like that. Okay, A is the amplitude of the vertical ground motion, and that's measured in micrometers. T is the period of the wave. With an earthquake, think of the earthquake starting at one point. They call that does anybody know what they call that? Where the earthquake starts from? Yeah, you got the epicenter, and then it spreads out in like a wave. Kind of think of like throwing a rock into the middle of a pond. It hits, that's the epicenter, and then you get this ripple wave effect coming out from the center. And what happens to the wave as it moves out from the center?
It gets smaller.
Yeah, it starts to decrease. All right. So if you had a pond that was like perfectly still, by the time that wave moves, say a huge pond, like 500 feet away, the ripple would probably be very, very small. So there's a factor that accounts for the weakening of the wave. And the same thing happens in dirt. You get that wave. And depending on, if it's like a mountain or bedrock or loose sand, that factor changes. Okay, so that's our formula for the Richter scale. And it's a logarithmic formula, okay, which we'll see what that means in a second. Okay, so our problem says that at the early stage of an earthquake, the amplitude of the vertical ground motion was A. By the end of the earthquake, it was 10 times as much. The vertical ground motion was 10A. I want to find the difference in intensity on the Richter scale. Okay, that's what we want to find, the difference in intensity. Now we're assuming here all other factors remain constant through the earthquake. The period of the wave isn't going to change. The factor that accounts for the weakening doesn't change. The only thing that's changing is the vertical ground motion. Okay, it's going to go from A to 10A. All right, so first thing, if you want to see a change between two values, what operation do you generally use? If you want to compare what something is now to what it was before. Yeah, you subtract, right? And we should subtract this so we get a positive number. So you think the intensity is going to be bigger at the beginning or at a later stage? At a later stage, the intensity will be bigger. So let's find the intensity, we'll call it later, minus the intensity at the early stage. Right, so our intensity is log of A over T. What's my intensity later? Later it was 10A. Plus the factor that accounts for the weakening of the wave, B. minus, okay, log of, what was my intensity early? Yep, early stage, it was A. Right, so that's A over T plus B. Now, why did I put that in brackets, you think? Look at what comes before. Yeah, that negative. I'm subtracting the intensity, but there's two parts to it. It has an addition sign, so I have to distribute. Okay. What's going to happen when I distribute that minus sign out? You see? Or let's just write it, and then maybe you'll see it. Plus B minus log A over T minus B. Yeah, what happens? B cancels out, okay? Meaning B has no effect on the final answer. And it shouldn't, because it was the same before at the early stage. It's the same now at a later stage. So it doesn't affect the final answer. Those are gone. So now we're just left with A and T. Okay, next thing I'm going to do is I'm going to break this logarithm up. Break it up into log and log. And I have a fraction bar. So how does that split? Addition or subtraction? Subtraction. So we have 10A and T minus. Now I'm going to split this up, but whatever I split it up into, I'm subtracting that whole thing that I split up. So what will that be, Corey? Log of? Anything I want to fill in here first?
A.
A.
And then, so we minus log of 2.
Log of T.
Plus log of 2.
Yep. And what's going to happen here? Corey's on the right track.
The log T will cancel.
Right. You're going to have minus log T minus minus log T. That's a plus. So what happens? Log T minus log T. So what we're saying here is T has no effect on the final answer. And it shouldn't. T is the same all the way through the problem. So it doesn't affect the final answer. So now all we're left with is log 10A minus log A. Okay. Now these two logs are separate. What could I do with them? Recombine them. And would it recombine as multiplication or division? Division. What would be on top? Bottom? And now what happens? A's cancel out. So the final answer, all I have to do is find the log of 10, which is 1. So the difference on the Richter scale, if something becomes 10 times more powerful, it's a difference of 1 on the Richter scale. Okay, so here's, I'm not sure, I think the Richter scale goes all the way up into the 8s and 9s. I think a 10 would crack the planet in half, so we won't look at that. But basically, each time you go up 1 number in the Richter scale, the effect of the earthquake is 10 times as powerful. So if you went from a 2 to a 4, how many times more powerful is a 4 than a 2? 100. 10 times 10. Or if you compared a magnitude 5 earthquake to a magnitude 2, the magnitude 5 is 1,000 times more powerful than a magnitude 2. You see the same scale with acids and bases in pH. Something with a pH of 4 is 10 times more, I can't remember if it's acidic or basic, but it's 10 times more than a pH of 3, or 100 times more than a pH of 2. That's how logarithmic scales work. Okay? So you might think, oh, 2, 5, they're basically the same thing. They're only 3 apart. Actually, they're like 1,000 apart. Big difference. Okay. Any question on that? All right. So the homework tonight, okay, it's on 2 pages. Okay, the first page is 293. It's 35, 36, 43, 44, 46, and 48. And then the second page is 301, and that's 15, 8 through 11, 16, 17, 23, 25, 28, 32, and 42 and 52. All right, so some of this is just on the calculator, finding a window. So that part you don't have to show, except write down like your mins and maxes. All right, so we'll go over that first thing tomorrow. And then tomorrow, I think what we'll do is we'll just do half a section. We'll do 6.1 part 1. And then we'll finish that up after Veterans Day.